Very good morning to all of you, and we are in the day 2, and today we will start a new topic. In our last 2 lectures, we were mainly focusing on the review parts of thermodynamics, which are basic equations, governing equations, fundamental principles, and we need to carry forward those equations in our real application for combustions. So, in last 2 lectures I had given some glimpses of some concepts which can be used as a mathematical tool for combustion analysis. So, next I am going to start something on this topic, which is called as combustion and thermochemistry. Why we say it's a chemistry part is involved, because in our thermodynamic discussions in our last things, when you talk about mixtures, so mixtures has its own identity before they are getting mixed, or substances getting mixed, and after also when they get mixed, we can find out the appropriate constituents in terms of their mass fraction, mole fraction, etc. But substance remains as it is. We can locate them in the reactants and after the mixture as well. But when you call as combustion, the reaction takes place between fuel and air, and the products are formed. That is what the chemistry concepts comes here. Normally, when you deal with the classical chemistry, we say reactants, products, and the reactions can happen among any kind of species that to form that products. But here our main chemistry focus would be that species that are involved in the fuel and in the air, and when they react, the final product that gets formed, that we need to quantify. So, that is the reason the word chemistry comes. So, combining thermodynamic aspects and combustions, a frequent word that is getting used is the thermochemistry. So, we will here also will start the our main focus for this lecture today is basic concepts of combustion and thermochemistry, how we can bring the thermodynamic concepts to the combustion systems. So, here we will discuss on this thermodynamics of combustions. We have reacting systems, then fundamental term that we normally use, what is called as adiabatic flame temperature. The concept of adiabatic flame temperature use the word that during a combustion process, what is the maximum possible temperature achievable, which means if you assume that reaction is happening in a reactor and some reaction is happening in a reactor, and we do not allow the products to go out with a concept that we have a perfectly insulated wall, so that whatever after the reactions the heat developed through these reactions developed through this reaction, we can quantify them, what is the maximum heat that we can get. This can be done by constraining the wall, that heat is not supposed to go out of the reactor. So, that is the concept what we call as adiabatic flame temperatures. Then we will talk about something on how do you model a reactive systems. Now, when a reaction happens, the reaction happens in a very short durations, and in this short duration there are many kind of elementary reactions that are formed, but ultimately when it comes to the final when the reaction settles down, we get the products. So, and what under some equilibrium conditions we call this the products, certain products are formed. Fuel and air, when it gets mixed, it is supposed to give these products. When you say this, that is called as a situation chemical equilibrium. When the chemical equilibrium is formed, then whatever products that are finally settles down, we call them as equilibrium products of combustion. We call them as equilibrium products of combustion. There is another concept which we normally use, that what is called as water gas equilibrium. It has a certain bearing that when for a combustion, any kind of combustion reaction, the final product is CO2 and water. If this happens, it happens, then we call this systems a concept called a water gas equilibrium. CO2 and water, they are in equilibrium after these reactions. Another important aspect of this combustion and chemistry part, when you talk about chemistry, the reaction can be exothermic or endothermic. Exothermic means heat is released, endothermic means heat is absorbed. But when you talk about combustion reactions, always you expect the reaction has to be exothermic, it gets released. Very rare situation we talk about endothermic, because sometimes the reactions, some species has formed at very high temperatures, but due to some reason temperature drops down and those species try to settle down by absorbing some heat within the systems. So, those cases the system may be considered as endothermic partially. Okay. So, those are the some of the concepts that we are going to discuss in our today's lecture. So, let me brief about this, that when you bring thermodynamics into combustions, the synonymous word we use is the thermochemistry, and combustion situation is nothing new. It is a very old concept. We can see that combustion concept was existing since the existence of sun, because that is the oldest mode because of combustion which is happening billion of years ago and will be happening in future. But still we do not know what is the source of energy. So, obviously when you say combustion, we have fuel and air. So, fuel somehow since we are getting energy from the sun, that means we can imagine there are plenty of fuels which are available in the sun, and that we are getting in terms of solar energy, we are getting these things. So, that means what I am trying to say, the concept is nothing new, it was a very old concept. Combustion concept comes to the human civilizations during the when we start burning the woods, when people see that fires in the jungles because of variety of reasons. So, those things were started with and wood combustion is a very is a solid fuel, and those combustions with starting point of that it spreads in variety of platforms, petroleum fuels, diesel fuels and all. So, with those evolution we can say what is the outreach of combustions, what was the outreach of the combustion starting from 100 years ago till date. So, that was one category of combustion. Apart from this, in our day to day life we have cookings, we use LPG, we use in our transport sector we use CNGs, Then there is another concept called porous media combustions, where the combustion concept comes only through radiation. And then this is about the application of combustions. Then moving to transport sectors, we started with IC engines, then we moved to gas turbines, then we went to rocket combustions. So through which the combustion concept is used mainly for thrust generations. So application is variety in variety way, just to harness the energy at the cost of getting some fuel and air mixing together or combusted together. So basic concept, when we start the combustion concept, we require fuel and oxygen. So in normal situation, nowhere we take oxygen separately to initiate combustions, as long as we are in the existence of earth. So requirement of oxygen comes from the air. But when you go to outer atmosphere, you might have known these things, that we carry liquid hydrogen, liquid oxygen on the system itself, because at outer atmosphere, outer space or deep space, we don't have oxygen or air. So basically, in the atmospheric level, we take the advantage of air to get oxygen, and when fuel and air when they are mixed together with addition of heat, we get a tremendous amount of heat which is get released after this combustion process is over, and we get some exhaust products. So identity of fuel and oxygen gets lost. So we call this that some reactants, they give products, and when they and these reactants here, they are in the form of fuel and oxidizer. So here oxidizer, I mean it's air as a whole, and we got this combustion products. Now when you say combustion, what really happens there? So how it initiates, and so this is initiated through a flame or non-flame mode. Through flame and non-flame mode means that when when you create a spark or ignite, we try to see, maybe in our last lecture, what Professor Marcus showed, that when you ignite, there is a flame plant that started moving. So that is called as a flame. So we introduce a term called as a flame, which gets which form instantaneously when we ignite the fuel and air mixture, and that flame travels in that domain. So basically, if you take a typical kind of IC engine combustion in a SI engine, so it's a flame mode. So we have initially a unburnt fuel gas mixture here, and through this we create some spark, the flame gets generated. So when the spread in the initial level, entire domain here is filled with fuel and air mixture. So when you create a spark, a flame front gets generated. So that is what we view or model the combustion phenomenon. So this flame front tries to move. So when it tries to move, because of its own strength move, it tries to compress this unburnt fuel and air mixture, and through this compressions the all subsequent fuels gets ignited. Now this intensity of, so initially it's a flame, so when this intensity of this flame gets increased and increased, we can emphasize them as a the flame front which is traveling at subsonic speed or supersonic speed. That way we can quantify as a detonation wave which is gets through this combustion. But initially the starting point of uh, uh, viewing this combustion initiation is through flame. Another way of is that which is a non-flame mode. Actually, this and this flame mode of combustions is typically a concept called pre-mixed. Pre-mixed means air and fuel are mixed before it gets combusted. So pre-mixed flame, that's what we sometimes we call this a pre-mixed flame. The non-flame mode type of combustions and diffusion flame, they are actually linked in a different way. Many people put it as either diffusion flame. Some people also call it as a non-premixed flame. But there are some concept here is that when you say non-premixed flame, what we see is that instead of the spark plug here is replaced with a fuel injector. When you have this fuel injector, what it means is that in this piston cylinder device, initially the compressed air is only compressed, and through this compressed air we inject the fuel. So fuel sees a enhanced pressure and temperature environment. So thereby the fuel gets auto ignited. When we say auto ignited, not necessarily that will have a particular locations, but here when you say flame mode, the flame prod gets initiated wherever you put a spark, and that started moving. But here, when you might have seen for diesel engine fuel injectors, we can put at various locations. Essentially speaking, we are creating multiple number of flames at a time, and they try to settle down together. So it cannot be categorized specifically a flame mode combustions. So that's the reason we call this a non-flame mode combustions, because flames can be formed at many locations simultaneously, because fuels gets auto ignited. Fuel droplets which are injected, they got auto ignited. When they got auto ignited, when they find a similar quantity of ratio of fuel and air, so we call this as the equivalence ratio. So when those numbers are at par, so the fuel gets auto ignited. So this is sometimes called as non-premixed flame. In many cases also it is interpreted as a diffusion flame, because initially it is a non-premixed flame, and this non-premixed flame also ignites the second layer of fuel air mixture which are subsequently. So the the flame front cannot be seen as a single front. It is a, so that is the reason the fuel air mixture gets diffused among themselves. That system as a whole has certain internal energy, but here during a combustion, when you interpret this internal energy, it is associated with three major factors. One is translational or kinetic energy of species, which are constituents of fuel and air. Then we have vibrations, this together with the vibrations and rotational kinetic energy. So actually we are bringing down this energy or breaking the fuel in atomic level as well as molecular level. So that is the reason internal energy is interpreted in this manner. And other aspect is that when you talk about this combustion, we normally refer for hydrocarbons only when you say it's a fossil fuel based combustions, which involves chemical reactions, dissociation, than their thermal analysis. Now moving further, the with respect to thermochemistry, we are also going to get acquainted with some terms, that is reactants, products and stoichiometric coefficients. I mentioned earlier that the reactants gives products, and to give the introductions that about stoichiometric combustions, when you write a chemical equations, balanced chemical equations, we introduce some terms like in this case H2 plus half O2 gives H2O. So that number of atoms both left hand side and right hand side matches, which means that total number of moles of reactants and products here in this case are not equal, because here it is 1 mole, here it is half mole and it is 1 mole. So this is way we, although number of atoms are same, but when you talk in terms of mole, there we write this equation in this manner: H2 plus O2 is equal to means here if you put in terms of their molecular weight. So this equation if you write, so this is 2 kg of hydrogen and 16 kg of oxygen will give 18 kg of water. So here masses gets balanced, and these masses are typically represented in terms of mole. So mole is the term that we are going to look at when there is a combustion reaction. Additionally, we have to introduce these stoichiometric coefficients for a balanced chemical equation. Then we will move to some concepts of fuel. So fuels are typically the fossil fuel, and they are mainly contain carbon, hydrogen and sulfur, and mostly the carbon constituents in the fuel is the major source of heat generations. And during a reaction, what happens, when what we call as a complete reactions, we try to see that carbon reacts completely to form carbon dioxide with air, and hydrogen it gives to water, and sulfur tries to give sulfur dioxide. Now, why these numbers are formed, why these constituents are formed? Because when the reaction is done, so after the reaction is over, the temperature always shoots up. When it shoots up, the carbon is no longer in a position to remain as its original identity. It tries to find or combine with oxygen elements to form carbon dioxide. Hydrogen has to give water, mix with oxygen to give water, and sulfur will have to give sulfur oxide. But at the end of the day, what we get is, if you don't get this, then we call this as an incomplete combustion. And here main culprits for this reaction, that if you do not get carbon dioxide, if you do not get water, and if you do not get when the sulfur forms sulfur dioxide. So when we don't have carbon dioxide, it will remain as CO. Why it will be there? That your the reaction environment is not that convenient or ambience to form the carbon dioxide. So this is how we should feel that how the reaction should go about. Coming back to fuel I mentioned earlier, it consists hydrocarbons, and we can call them as a solid fuel, liquid fuel, and gaseous fuel. Solid fuels, we started with wood, but it can also go to, means if you are going to concentrate the energy with a small density environment, then you have to bring it in the solid form. Firecrackers, they are in solid forms. All kinds of solid propellants, they are also solid fuels. And for liquids, we have gasoline, diesel, kerosene, fuel oil, all they fall under liquid fuels, and we call them as liquid hydrocarbons. Again, when we say gaseous hydrocarbons, the major constituents we find them in the methane. So what I am trying to say is that it is essentially hydrocarbons which are available in different phases. Then oxidizer. So I mentioned that oxygen is required for every combustion reactions, but its usage, extracting the oxygen from air is not possible or lucrative. So it is better that you take this oxygen from air. But when you take oxygen from air, air has these major constituents like nitrogen, oxygen, argon, CO2, so many other components. But major component is 78% nitrogen and close to 21% oxygen. So initially, when you look at fuel and oxidizer systems, if you take a fuel as a methane and it reacts with oxygen, it gives a CO2 and water. But since in actual reactions we are getting oxygen from air, so instead of this we write that equation in this form, like O2 plus 3.76 N2, and why that number comes? Because of this ratio. So ideally speaking, they should give CO2, water, and nitrogen should not react. So nitrogen comes out as it is. So this is how the complete combustion reaction should look like. But in reality, this normally doesn't happen, because this is possible only when you have this is possible when this equation is balanced, and for this balanced equations we use this stoichiometric coefficients. But if the reaction doesn't happen to form in this manner, which means the composition or the stoichiometric coefficients of fuel and air do not match, then we will end up having different components. We may not form CO2, we may not form water, then what else will form? So those cases we will end up forming this NO, NO2, because this N2, which has to be go as a whole, because of the elevated temperature, it tries to recombine with oxygen to form these kind of constituents, and they are actually the culprits for the air pollution. So here we are going to use the word stoichiometric many times in this course also. We will be using this term stoichiometry. Stoichiometric means it is the correct or exact air fuel ratio that is required for a combustion to happen, for a complete combustion. So we normally use the term as air fuel ratio, or we also interpret in terms of fuel air ratio. So here there is some logic here, that when you use the concept of IC engine, normally frequent term is air fuel ratio. Frequent term is air fuel ratio. But when you enter into gas turbine combustions, people use fuel air ratio. There are some logic is that I mean it's both are same, interpretation for them is both are same, but what typical requirement for gas turbine combustions, because the those fuels are very costly. When they are very costly, people actually rightly trying to find out, instead of air fuel they call it as a fuel air, because they want to know that what is the exact quantity of fuel that is getting utilized, or what is the exact quantity of the fuel which is not utilized. So, in gas turbine combustions, the fuel air ratio becomes frequent, even rocket combustion as well, but of course there they have using solid fuel. So, that way we air fuel ratio and fuel air ratio terminologies are same, interpretations are different. So, in one case we say air fuel ratio with respect to mass of air to mass of fuel, other case we say fuel air ratio with respect to fuel to air, mf by a, ma. Then there is a term called is theoretical amount of air. For a reaction to happen, I say oxygen plus nitrogen, they constituent, they form as air. To ignite certain quantity of the fuel, we require exact quantity of air. So, that air we call it as a theoretical amount of air, and that theoretical amount of air we call it as a stoichiometric quantity, that is a frequent term. This stoichiometric air, using, if your combustion process does not use exact quantity of theoretical air, then mixture is treated either lean or rich. The word lean, which means everything that is with respect to fuel, means if it is a lean mixture, it is interpreted that fuel is less, air is more, and vice versa. So, fuel lean or fuel rich, those are the two numbers that we are, those are two terminology that we will be using along with this stoichiometric value. Other ways of interpretation of percentage of excess air. So, if it is a theoretical air and percentage of excess air, which means it is a fuel lean, and percentage of defines fuel lean or fuel rich combustion, I mean, or percentage of fuel excess air means it is a fuel lean, percentage of deficit air means it is a fuel rich. So, so for example, if I say 150% theoretical air is equivalent to 50% excess air, which is a lean fuel, 80% of theoretical is equivalent to 20% deficit air, which is fuel rich. And all this air fuel ratio or fuel air ratio, we write mathematically in this form. Let us say if we say air fuel ratio, it is Ma by Mf, and this Ma we can bring them to their molecular weight and number of moles. Then we find this particular number Na by Nf, we can say this is, by definition we can call this as in terms of molar air fuel ratio. So, that way we normally interpret our analysis, in what way we are interpreting, either in mole form or mass form. Then we see something in this term, like when the reactants are formed either lean or rich, we define a term what is called as equivalence ratio phi, and that equivalence ratio phi is based on the ratio fuel air ratio to the actual value to the stoichiometric value. So, in reality it can be fuel lean or fuel rich, but in actual case which is the actual case, in a stoichiometric case it is based on this, based on the fact that we get exact quantity of theoretical air. Then we introduce whether it is a fuel lean, phi is less than 1, when it is a stoichiometrics, phi is equal to 1, and phi is greater than 1 when it is a fuel rich. But here the summary of these things is that when you have a fuel lean, we will get oxygen in the products. When it is a fuel rich, we get CO and unburnt carbon, unburnt fuel in the products. And rightly say that when you have a stoichiometric conditions, we get the maximum maximum energy, which exactly talks about the situation where we can find out the adiabatic flame temperature during a combustion process. So this is some class examples how you look at methane air combustions for rich lean fuel and some combustions for rich fuel and so on. So this is nothing new here, just to make a balance, and whatever I have said here, that in a stoichiometric combustion we get CO2 and water, and in a non-stoichiometric cases or fuel lean or fuel rich situations, we will have either NO, rich fuel we have CO and unburnt fuel, and in the lean fuel we will get excess oxygen. Then we have these products of combustions. So for a situation where in a methane air combustions we get CO2 and water and N2 remains as it is, what we see is that in the products of combustion we get water, and when we say it is water, the analysis or interpretation little bit different. That one thing we say that if we take the products of combustion as a whole with CO2 and N2 without considering water, that is also possibility. Other way is that you take this water into account. So those cases we call them as a dry product analysis or wet product analysis. And in some situations it happens that gaseous products of combustions in the mixture are cooled to a dew point of temperature. Means basically why this water is formed, that when the products of combustions finds an environment or a cooling environment, so that they try to condense with deposition of water, then we call this as a then we reach that reaches to their dew point temperatures, so condensation gets initiated. Then we will try to give the introduction to the standard reference conditions when you actually deal the combustion mechanism to happen, and the standard reference mechanism could be either reference condition atmospheric pressure and reference temperature is normally done at this number. Why this is required? Because in our thermodynamic analysis calculations we require the formation of the products with respect to some references. Those formation of products are taken at these references, if no, and all the data that are available in the books, they are with respect to the standard reference state, and mainly this data is required for computation of absolute entropy. So here these equations I have shown in the last class, where we try to define a mixture, and here we are saying that mixture is not a mixture, it is a reactants and products, and those reactions and products we are quantifying with their parameters, internal energy, enthalpy, entropy for each constituents and try to make a balanced equation. So, what we see here that while computing entropy and all these equations, if we find, we use this in molar form, number of moles for each of the species or constituents. And when it say this some species are formed, how it is formed, it has to be dealt with, because when you do the entropy calculation, it talks about the difference between initial state and final state. Now, the initial state and final state, when you do analyze for a mixture, it is easy that because they do not react. Now, when the reaction happened, your identity of reactants is lost. So, people try to interpret that how to find out this change in entropy. So, they started with concept that we have to take some reference value P reference and T reference, which is that reference conditions. You take that reference value as identity for calculation of entropy, and that from there you calculate the entropy change. So, the analysis gets simplified because if you look at a classical thermodynamic equations, S is equal to S2 minus S1 is equal to this and it is entropy. You do not really bother about this term, we really bother about this R bar ln Pi by P references. But here we have to bring absolute entropy into discussion. This is enthalpy of formation. So, another term we say how do you get the enthalpy of formations. In this, while defining this term, we are actually using the first law analysis, reactant products. So, something like here we say we have a reactor and some species that enter, and while going out we get the different things, but entire reaction takes place at these reference conditions. So, this means that if you say formation of C at this reference and formation of CO2 at this reference, so that those reference condition match between your inlet condition and outlet conditions. When they match, we frame, first thing we find out the chemical reactions, do their molar analysis, and then find out the difference between the enthalpy of formation, which is defined by this term H bar CO2 through these equations. So, ultimately for any reaction, enthalpy of formation of CO2, like in this case it is CO2, is nothing but which is heat transfer by number of moles, which means this heat transfer can be negative or positive depending on exothermic or endothermic. That way we say it is an enthalpy of formation for that species. We say NO2 is formed, CO is formed with respect to C and O. Then with respect to that enthalpy of formations, because the word enthalpy of formation is with respect to species, but as a whole, when you take the fuel as a whole, we interpret in this way that we first think about what is the enthalpy of combustions. So, enthalpy of formation is with respect to species which is formed. Enthalpy of combustion is with respect to reactants and products. When you say reactants and products, you try to find out using the first law, you try to find out what is the energy content in the reactants and what is the energy content in the products. Difference between them gives the enthalpy of combustion. And this enthalpy of combustions is linked to the heating value of fuel. How do you interpret? So, heating value of fuel, enthalpy of combustion is with respect to chemistry, but with respect to fuel we call them as a heating value, and heating value of the fuel, it is interpreted in two ways. One is higher heating value, other is lower heating value. Now, when the analysis is done keeping water in the products, combustion products, uh, um, and one case we call this as a higher heating value, and other case when the when you say higher heating value, it is obtained when all water formed by the combustion products is in the liquid form. So, that way the consideration of water formation is taken into account during the combustion process. Now, this when we say lower heating value, it is recognized when all water formed is in the vapor state. So, that means one case we say the formation of products without formation of water, and other case we say the formation of products and when water is formed or condensation takes place. That means the reaction temperatures, that means products are cooled below the dew point, their dew point temperature. Then I mentioned earlier that when reaction happens with some fuel and air, what we see is that if you enclose that complete environment, then we get a case where entire energy gets contained within that domain. Now, when those energy gets contained in the domain, the maximum possible temperature that can be raised through this process, we call this as a adiabatic flame temperatures. So, this is a adiabatic word is just a concept that to calculate the maximum temperature during a combustion process. So, this is also similar to this, using our governing equations, how one can calculate the adiabatic flame temperatures. Now, while calculating these adiabatic flame temperatures, what we interpret graphically in this manner, that entire energy of reactants gets transferred to products. So, when you start this enthalpy versus temperature curve for all reactants and all products, they will go in this manner. That means initially the reaction starts here at one point. Slowly, when the reaction happens, the number of moles of reactants come down, products formation goes up. So, that way the temperature also in this axis keeps rising, and one particular time when the reactants are completely burnt to form the products and we do not allow that heat to go out of that domain or reactor. So, those enthalpies are balanced. So, in those cases, whatever temperature we reach, that is called as adiabatic flame temperature. That means initially we start with Ti and finally we arrive at this point, it can be maximum temperatures. So, this is how we analyze the adiabatic flame temperature in two ways. One is adiabatic flame analysis at constant pressure, other is at constant volume. So, I mentioned in our thermodynamic equation from the first law. So, if the first law is to be satisfied, that there is from the first law analysis we can say reactants and products they are equal, because I told that the internal energy is a function of temperatures. So, from the first law we start with internal energy for reactants and we try to say that they match, and while calculating that internal energy we bring initially they are at initial temperature Pi and Ti, and when final products are formed, it is formed at adiabatic flame temperature and final pressure. When this equation matches, then we can calculate the from this equation we can calculate these two values, one is at constant volume, other is at constant pressure. Okay. uh, and this internal energy can be represented in terms of enthalpy as well, because U is equal to H minus PV. Okay. So, interpreting adiabatic flame temperature can happen in two ways, one at constant volume, other at constant pressure. So, based on this, we have two equations. One equation is this, where uh, where we call this in terms of enthalpy, which is calculated. The adiabatic flame temperature is calculated at constant pressure. Now, having said this, adiabatic flame temperature calculation at constant pressure and constant pressure and constant volume, one can find out some of the important inferences, that during a combustion process, when you calculate this, use this word, we can say that adiabatic flame temperature gives the identity of maximum possible temperature, and that temperature, if you say you calculate at constant volume, it is always higher than that of constant pressure. And this has similar logic when you deal the analysis of Otto cycle and diesel cycle in an IC engines. One is a constant volume based combustion, other is a constant pressure based combustion. So, these are some of the inferences that we get out of it. Then there is a concept of absolute entropy. This part I have already explained how you are going to get it for a mixture by considering the reference point of pressure and temperatures. Now, coming back to modeling of reacting systems, there are two approaches. One is a constant volume modeling, other is a constant pressure modeling. So, in this constant volume modeling, we take care about main chemical reactions, how it happens, and this is a simple generic form of chemical reactions for hydrocarbons, where we say these subscripts of carbon and hydrogen in a general form A and B, and this A and B are and through this equation, putting A and B in some manner, we can frame a real combustion equations. So, while doing this, one can think of a constant volume based modeling, which allows the heat transfer as well as heat transfer into the systems, because we are through this process we are igniting. Other way that fuel air enters to a reacting domain. At the end of the day, we have some fuel sitting into here, air enters, when the heat is added we get the combustion products. So, this approach is a constant volume based modeling. And in a closed system modeling, normally we start with this kind of constant volume based modeling. For a closed system modeling, we get our analysis through this constant volume modeling by considering using the advantage of interpreting internal energy in terms of enthalpy. So, in this equation we start with this equation, but somewhere this U value is interpreted as H minus PV. PV is nothing but your RT. So, these are the equations which are available in the books as well as in the slides. One can interpret in this manner. Then we have to deal with the entropy balance again for an open systems, and subsequently it can be interpreted for the closed system as well. And why I am trying to link is that all these equations which were given in our last lecture was used to derive this form, and here we are not going into the derivations, rather end use of these equations can be directly interpreted for modeling of any kind of combustion system. Here moving further, it is a closed system entropy balance. So, for that we need to recall the entropy equations from the thermodynamics, and assuming that reaction is going to happen in a closed systems with Q no heat additions. Okay. So, that way we did this, we have to do this analysis in that manner. And coming back to the chemical equilibrium part, when the reaction happens, when you have a ideal combustion, we have CO2, water, O2 and N2, but when we do not have those things, we have intermediate products like OH, CO, OH and N, NO, these are intermediate products. When such things are formed, and the final, it is a these are the actually dissociated species, and they try to see another environment to form CO. If they do not see, they remain as it is there. So, if these are the things, so that means equilibrium has not happened. Now, moving further, this is a classical example how we say that during a chemical, when we say it is a chemical equilibrium situation, we land up having a case that when you actually view a reaction between CO and O2, it has to give CO2. But the formation of this CO2 from this, what actually initiated this reaction? So, initially we write this equation in this manner with a case that all of a sudden CO and O2 does not come together. So, when you see this equation, it is equilibrium equation. Had this equation been non-equilibrium, at any given instantaneous time, if you look at this equation, we introduce a term that at least 1 minus alpha, alpha and this. So, when alpha is 0, there is no formation of CO. So, this is how you introduce these equations separately in the modeling to this analysis, and that alpha we call them as a dissociation fraction. This is again same case, when alpha is 0, it means maximum heat release. When alpha is 1, that is no heat release. There are some significance of interpreting equation in this manner, because when the combustion modeling are done in the softwares or on your own, you have to start the equation, write the equation in this manner, putting its end conditions. Okay, so this is a case where we try to interpret a chemical equilibrium situation for a simple reaction system from CO and O2, which means that when the reaction proceeds, we can see that how the fraction of CO2 gets dissociated, that means how this parameter 1 minus alpha changes during a reaction. Now, when you say it is a chemical equilibrium situation, which means that at that point of time entropy, because entropy drives the reaction, reaction proceeds in the direction of entropy. Simultaneously, we calculate the temperature as well as entropy. So, when we have, how do you calculate? I have told the reactions, the reactant and products you have to take different entity, each term you have to calculate, and for each cases you have to do the energy balance through this process, and we can say that entropy always increases in the direction of reaction. So, this curve we get side by side. When the reaction proceeds, temperature also increase because this dissociation fraction gets changed. So, this curve also keeps on increasing. At what particular time we reach, we have this final temperature, and this final temperature, if the walls are adiabatic, this final temperature can be interpreted as adiabatic flame temperature. Now coming back, when the equation settles down, that means when equilibrium is achieved, which means that reaction cannot proceed further. So you have achieved the equilibrium temperatures. So the point at which we have maximum entropy, if you drop a vertical, then it will cut this curve and this will give you the equilibrium temperature. So this kind of graphical analysis was mainly used basically when we don't have any other softwares or modeling approach. So this is all I have already explained. That additionally, I have also forgot to mention that another term which is a Gibbs free energy, that many chemical, or normally we say Gibbs function. The Gibbs function plays a vital role during a reactions because entropy is one parameter. Gibbs function gives a different approach which consider temperature and pressure as well simultaneously for this analysis for the combustion process. So something on this already I told for equilibrium products of combustion. In this equilibrium products of combustion, for a if you say propane air mixture, one classical examples, the intermediate pressures for these things are different, like OH, NO, and when you take this mixture globally, when equilibrium is achieved, we get this equation, CO2 and water. This is a classical curve that talks about these equilibrium products of combustions for a propane air mixture. So here the significance of the curve is that in a single curve or single graphical representations, we can talk about mole fractions, we can talk about maximum temperature, also we can talk about the range of equivalence ratio in which the reaction is going to happen. So if you see here, in reality, and for a propane air mixture, if you take ideally at equivalence ratio 1, you will reach this adiabatic flame temperature, but in reality that normally doesn't happen. It happens somewhere at phi is equal to 1.05. These numbers we get for a realistic experiment, and corresponding to this we get the flame temperature as 2278 Kelvin. So for all IC engine application area, whether you do constant volume analysis, constant pressure analysis, your adiabatic flame temperature falls in this range. When you go to gas turbine combustions, these numbers will be different. This is one part. Coming back to the formation of the products, so when you have equilibrium based combustions, we have CO2 and we have water and CO2. As you see that when your equivalence ratio is increasing, CO2 is also increasing, then it falls down because it doesn't find because the concentration or mole fraction falls down, and here similarly for these things. But this is what you see as a final entity. But before they form, before this H2 and CO2 form, already CO formation would have started. Hydrogen H2 would have reacted with oxygen. So these are some of the intermediate reactions that gets built up during the initial phase of reaction. Finally, it settles down with this. But what we see globally is something like this curve and this curve as a chemical equilibrium equation. This is similar curve. Here also I mentioned about adiabatic flame temperature, and one point is that 1.05 is gives you the maximum temperature, but one point of time your water corresponding this highest mole fraction of water at equivalence ratio of 1.15, which means that this at equivalence ratio of 1.15, it is expected that we can get maximum mole fraction of water. These are same in continuation with that. There is nothing new, I have already explained. And the finally products of combustion, what we say here is that this is a complete picture that talks about all intermediate species that are formed during a lean phase of during lean phase and rich phase. So in that case, what you see, this curve shows how intermediate species like OH, NO, H, CO, NO and all this started, and they started with this at this point, and then when they keep on when the reaction proceeds, this NO formation, and by that when the NO formation starts also, simultaneously OH and CO formation would have started. So all the curves plotted together, which means that species evolutions during a combustion reactions, this particular graphical representation is going to talk about. So this is nothing new here. And finally, lastly, I will just talk about a water gas equilibrium case, that normally when you have end products of CO which is completely undesirable, so many industry they talk about how to reduce this CO level, though they consider a water shift reactions, like they create an environment in the final product domain that CO, when there is a formation of CO and if it sees enough water, then it proceeds to formation of CO2. So they create a typical environment at the product level, so that we can shift the propagation of CO to CO2, CO to CO2. So this is what we call as water shift reactions, and all in most of the industries they use this concept to reduce the level of CO, which is mainly culprits for pollutions. So already it is time, maybe we can continue after this, or I will continue in this second half from there, because I have some more slides to show. Or maybe a few minutes if it is there.
So
Last point I am coming back. So here when you I mentioned about these water shift reactions. While dealing with water shift reactions, another added advantage or added important concept is that we find the equilibrium constant, because when you analyze the hydrocarbon equations, fuel and air is taken with respect to oxygen and nitrogen, we arrive at these particular equations when on such reaction happens in a situation that we have formation of CO, oxygen H2, H2O, CO2, which actually means that these equations are getting modeled as if a reaction is going to happen in a generic manner, and all the products are trying to form simultaneously with this term. Then how do you evaluate those stoichiometric coefficient values? So for that reasons, we introduce a term Kp, which is called as equilibrium constant. This equilibrium constant normally we find with respect to ratios of various species that are formed. So why this equation is required? Because by doing this atomic analysis, we can find out X, Y, A, B, C, D from both sides. So one chart we can prepare: left hand side carbon, number of carbons, right hand side carbon, left hand side oxygen, right hand side oxygen. So all these things we can find out. And you will find, and if you want to solve all the equations, you need to see that number of unknowns and number of equations are same. So here, to do that, what we that thing is coming here, that when for a given situations, when you have this particular case, we do this atomic balance, we find all the stoichiometric coefficients, then from there we can analyze all the total number of moles based on the unknown points of X, Y and Z. Then through this process we can get about the typical constituents of mole fractions of various species. One is CO2, CO and water. What I explained those cases, that when that reaction that happens, it is a lean and stoichiometric. When you have lean and stoichiometric, we have these products, CO and CO2. But when you have rich combustions, fuel is not getting sufficient air to combust properly. So in those cases, so the reactions has to be modeled in a similar manner. We will have large number of equations like balancing C, H and O atom, we get number of equations is equal to number of unknowns, and through the introduction of equilibrium constant Kp, which is evaluated based on the values of partial pressures of each constituents. So thereby we get a set of equations, and through that set of equations, by doing this analysis, we get this kind of curves. So what I am trying to say is that when you generate these curves, actually background we are using all these equations that gives you a pictorial or graphical representations for variety of species formed during the evolution of a chemical reactions. So this is all about I am trying to say in this lecture. There are some sample problems in this lecture, so that can be used to get the understanding of what has been covered in these lectures. So ideally, at the end of these things, I will just try to emphasize, although you see these equations, unless and until you try to do on your own, you will not get a feel out of it. For example, one case I can say, if you want to calculate the adiabatic flame temperature, unless and until you really do these actual calculations, you will not be able to evaluate these numbers. So this is a case, specific case that talks about when you really use those enthalpy of reactants and products, try to map with the data books from the with data tables from the book, really calculate adiabatic flame temperature and two situations, one is constant pressure and constant volume. We will find that at constant volume value will be greater than the constant pressure. So this is I am trying to emphasize, if you do it, then only you will get a feel of interesting approach. So with this I will conclude. Thank you for your attention.